Next, by taking the same analogy as we have done in the arithmetic progression, there's a term defined as GM, or the geometric mean, which says that if we insert a number capital A between two numbers A and B, such that A, G, and B are in GP, then G is called the geometric mean of AB. Now, to calculate G, we'll use the basic property of geometric mean that says that the ratio of the consecutive terms remain constant. That is to say that we have this particular relation which gives us G is equal to root AB. Okay. So likewise, as we had in our arithmetic progressions, we could insert n n geometric means between our two numbers. So let's say they are represented by a1, a2. So, um, let's just assume that these are g1s. It would be easier to just memorize them if we take them as g1 and not a1, because it may clash with your understanding of the concept of the arithmetic means. So let's take what these particular geometric means as g1, g2 dash dash dash, and gn. Okay. So if we insert n numbers between a and b and say g1, g2, gn, such that a, g1, g2, gn, b are in gp, then these particular numbers, that is g1, g2, and dash 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 gn, are called the nth geometric mean of the particular numbers, that is a and b. So to work out this, we'll again write the general terms formula, and the the last term b will again be the n plus second term, that is t n plus 2th term. Okay, so next we move on to finding a relation between the arithmetic mean and the geometric mean. So to find the relation, let's first of all write what is a minus g. Uh, this is a relation which holds that the arithmetic mean between two numbers, let's say we have two numbers as AB, and their arithmetic means are respectively A and G. So we'll note that the arithmetic mean is always greater than or equal to G. So to work this out, let's take their difference, A minus G. We'll obtain A plus G upon 2 minus root AB, which if you take the LCM would come out to be under root A minus root B the whole square upon 2. So since square of a number is always greater than or equal to 0, we have that A minus G is always greater than 0, and which gives us the required relation. As you can see, the equality holds when the square is equal to 0. That is to say that the root A is equal to root B, or in turn A is equal to B. Okay, so now after studying the general patterns, we moving on to some of the very natural series which we come across. That is, first is root sigma k. That is to say that it is equal to let's write down the series is 1 2 series is 1 plus 2. Let's start from again. The series is 1 plus 2 plus 3 plus 2 till plus n. The first series is this. Second series, as you can work out just by putting the values of k from 1 to n, is 1 square plus 2 square plus 3 square plus till n square. And the third and the last series in this particular special series sequence is that is 1 cube plus 2 cube till n cube. So in this particular segment, we'll look into how to find the sum of the particular series, and generalize this concept to finding the sum of sigma k cube, sigma k to the power 4, sigma k to the power 5, and so on. So let's first of all look into how to get sigma k. So let's first of all, this is the answer result which we'll be going to prove. So simply, as you can see, this series is an AP. This series is an AP as the difference between any two consecutive terms is equal to 1. So you can simply work out its sums formula by taking the first term is at 1 and d also equals to 1. So let's try to find out its sum. So the number of terms will be n. So n by 2 into 2 into the first term plus n minus 1 into the common difference, which is equal to 1. So we have the formula as n into n plus 1 upon 2. Okay. So the next series we have in our particular sequence is sigma k square. So to work out its formula, let's first of all see what's the formula. This is the formula, n into n plus 1 into 2n plus 1 upon 6. This is the formula for the sum of this particular series. So to work the formula for this particular series, what we consider is this identity. A identity which has the which contains the difference of two particular sequences, k cube minus k minus 1 whole cube. So these are the two particular numbers consider, and as you will see, the power here, that is 3, is one more than this particular power 2. So we'll always use this generalized property. We'll take the difference of two numbers with only a higher degree than the particular sequence of which the sum has to be found. So we'll take k cube minus k minus 3 k minus 1 whole cube as our identity, and if you simply expand k minus 1 to the power 3, you will get 3k square minus 3k plus 1. So just put in the values of k from starting from 1 to obtain 1 cube minus 0 cube equals to 3 into 1 square minus 3 into 1 plus 1, and so on. So you will have this particular type of series. So if you add on the RHS together of all the particular equations and the corresponding RHS also, so you will see that the terms will cancel out like this, and you will be left with only n cube. So what we will have is n cube minus 0 cube equals to 3 sigma n square minus 3 sigma n. So sigma n, you know, it's n into n plus 1 by 2 plus n. So basically we have this particular thing. We have just manipulated this and taken 3n square this time to the LHS. So to after simplifying this particular expression, we have 2n cube plus 3n square plus n. So after factorizing this, we have sigma n square equals to n into n plus 1 into 2n plus 1 upon 6. So it's basically what this identity is the key. We hold our proof to this identity. So just remember to consider the cube, the number, the difference of the just a single higher power of the sequence, then of which the sum has to be found. Okay, so now to work out sigma kq, we'll consider k to the power 4 minus k minus 1 to the power 4, and get and just try to derive its expression by expanding k minus 1 to the power 4. You can do this either by simple multiplication, or you can use the binomial theorem to expand this. So we'll obtain 4k cube plus 6k square plus 4k plus 1 here. Now putting in the values of k from 1 to n, we'll obtain something of this sort. Here you will have n, it's just mistaken here, you will have n minus 1 raised to the power 4 here. So these terms will cancel out, as you can see. If you put the values of k as from 1 to n, only the term remaining will be n to the power 4. So we'll have n to the power 4 minus 0 to the power 4 equals to 4 sigma n cube, where the values of n tending from 1 to n. Okay, plus 6 sigma n square plus 4 sigma n plus n. So just manipulating it, just taking all the terms to the RHS here, we'll have 4 sigma n cube plus equal to n to the power 4 minus 6 sigma n square minus 4 sigma n minus n. Now using the formula for sigma n square as we have derived earlier, we have n into n plus 1 up into 2n plus 1 by 6 into 6. So this 6 and 6 cancel out. We have simply n into n plus 1 into 2n plus 1. And again putting the value, formula for sigma n, we have minus 4 n into n plus 1 upon 2, and 2 and 2 cancel out. We have only 2 here. And after this expression, just expand this and find a simple expression like this. So finally you would have formula of this one. So this is the formula for sigma n cube. Some of you might have got confused here that I've used the term sigma n cube instead of sigma k cube. Just keep in mind that it's a dummy variable. That is, if you put n equals to 1 to say n here, what is that? That's you have to put the value of this particular n from 1 to n. You can use another variable, say if you're using k, so these all terms will become k then. So this has nothing to be confused about, it's just a dummy variable. Thank you friends. In this video tutorial, we talked about sequence, series and progressions and some of the special series. I hope this was useful.